Now, the next problem I want to tackle is that of outliers. What happens if in your data you actually have some outliers with respect to the distribution of values in your participants. And this is a wonderful paper by Mark Woolrich of the FSL group. And what they did is they both simulated and then looked at actual data under different circumstances in terms of the means and the outliers that you might get. And they then compared 4 different analyses. One is just your regular ordinary least squares. One is known as a mixture of Gaussians. It's the idea that you try to model your group data as coming from 2 distributions, 2 Gaussians. One is your actual data, and one is the outlier data. So you try to model separately these 2. You try to model separately the noise term, essentially. Then they also looked at what is known as the bi-square approach. A bi-square approach is an iterative approach. Essentially, it's a form of iterative weighted least squares, where you use you run a regression, and then you look into the data, and what you do is you downweigh the pool of observations that have very large errors. So in other terms, if there's a very large error, what you do is you take note of that big error, and then you downweight the pool of that particular observation. And you keep doing this until you meet some criterion that tells you that there's no error big enough that you need to further downweight it. It's just an iterative procedure where you keep sort of downweighting observations that just give errors that are too large, which implies that they are outliers. And then finally, the last one we're going to look at is known as randomize, and it's a non-parametric approach. I will explain, I will give a demonstration of how these type of permutation testing works a few slides down. So for now, just bear with me. So the first example is if you have no effect, or a mean of 0, and no outliers, the estimated group means you can see is pretty much the same across OLS, the mixture of Gaussians, or the bi-square iterative approach. And here randomize is not shown. Now, what happens if the mean is 1, and then we also have a positive outlier? The mixture of Gaussians and bi-square do pretty well overall. Despite the presence of a positive outlier, you can see that their mean is somewhere down here, so possibly close to 1. Whereas if you look at what happens to the OLS, it has been pulled up dramatically by the presence of an outlier. So as soon as we have an outlier in the data, the OLS clearly fails. If you look at the case where we have 2 positive outliers, the mixture of Gaussian and bi-square still do pretty well. You can see that the mixture of Gaussian is getting pulled a little bit up by these up here. But by and large, both these approaches that do try to address the issue, be it by modeling outliers separately or by downweighting outliers, they do cope pretty well, even with 2 outliers. Whereas this is out of a group, I should say, of 20 observations, of 20 participants, that would be. Whereas our OLS got pulled up even further by the presence of 2 outliers, out of 20. Now, if you add a negative outlier, you can see that exactly the same thing happens. Our OLS gets pulled down, whereas our mixture of Gaussian and bi-square are still doing pretty well overall. And this is the one we saw before. So overall, it's pretty clear that ignoring outliers can lead to dramatically misestimated group means. Now, to further look into this, what they did is they first simulated data. They simulated a group of 20 volunteers, in this case with a mean of 0. And what they did is they looked at, as you add outliers, just like before, how does that affect the proportion of false positives? and false negatives. And what you're seeing here in this graph, if you were perfect, this is a log-log graph. If you were perfectly on this line, it will mean that your false positives are exactly 0.5. Whereas if you're on this side of the graph, then it means that you're getting false negatives. If you're on this side, it means your false positives are greater than the nominal than the nominal rate. So with no outliers, all of our 4 randomizers, also shown now in blue, all perform pretty well. But as soon as you add a positive outlier, and these are simulated data, by the way, you can see that whereas randomized remains fairly loyal to sort of our optimal, right, our desired outcome, all the other, most other approaches, so this is your conventional OLS, this is the bi-square, and you can see here the mixture of Gaussian is still doing pretty well. But clearly now we are suffering from issues in our inference making. If you look at real data, then again, under no outliers, indeed confirming what we saw before, all methodologies tend to do pretty well. But as soon as we add a covariate outlier, now we get really terrible inflation of false positives under the bi-square. We get quite some inflation also in the mixture of Gaussians and OLS, whereas once again, the non-parametric approach is the one that continues having perfect false positive rate control. So before moving on to the next and last section, which is about the interaction between assumptions, parametric assumptions, and corrections for multiple comparisons, let's just take stock of what we discussed so far. What can you do in order to mitigate these issues of violations of the distributional assumptions of parametric approaches? Well, you can probably take at least 3 strategies. For one, you can ignore it, which is more common than you'd think. And quite frankly, any software you use will allow you to ignore this if that's the type analysis you want to do. SPM will allow you to ignore it. AFNI 3D t-test will allow you to ignore the problems of heteroskedasticity and other such issues. And FSL OLS, if you do a group analysis with the OLS option, that will also allow you to ignore it. And I would not recommend that you do that. A second approach would be to, with any of these 3 softwares, AFNI, FSL, or SPM, you can use options that incorporate the variance from the lower level into your group level analysis. In other words, doing something akin to a mixed effects. So always more desirable to do a mixed effects analysis because it tries to take into consideration the within subject variance. On top of that, and SPM will allow you to do that particularly by the use of a restricted maximum likelihood approach. AFNI has a tool called 3D MIMA, if I remember correctly, that will allow you to do something akin to that. And FSL, of course, if you use the Flame option, whether you use Flame 1 or Flame 2, it will do it in both cases. But Flame will actually implement a true mixed effects, as we have discussed a few lectures back when we're talking about group analysis. On top of that, FSL also has a very practical button that will allow you to enable the de-weighting of outliers. In other words, it'll produce a robust regression. So if you want to boil this down to what does it mean in terms of our regression, it really means that what you're doing is a weighted least squares. If all you're doing is you're using the mixed effects in order to correctly account for the variance on the main diagonal of the variance covariance matrix. Or if you also have outliers, then it means that you're doing really a generalized least squares because you're messing with the off-diagonal elements of the variance covariance matrix. And this is definitely using a mixed effects is definitely a very good option. Although, as you have seen in the paper we just discussed, both the de-weighting of outliers or any iterative process don't always fix problems with outliers, at least not entirely. And finally, you can use what a lot of people seem to be recommending these days, which is just do away with the distributional assumptions of your analysis. Do away, use a non-parametric analysis. Typically in fMRI, we seem to have gravitated towards permutation type non-parametric analysis, although there are other perfectly legitimate ways of doing it. And do this and forget of all of these assumptions. You don't need them anymore. The beauty of it, of course, is that it doesn't depend on the paradigm you use. It doesn't depend on smoothing. It doesn't depend on whether you care to make inferences at the voxel versus cluster level. So it's a very practical, and at least theoretically, it only depends on exchangeability, which I'll get to a few slides now. And also on top of that, I should say there are existing software that will implement this. SPM has a software called SNPM. FSL has a software called Randomize that allows you to do exactly this. There's a wonderful software called Broccoli, which is much faster than FSL because it uses the GPU, and it also allows you to do Bayesian analysis at the first level, and maybe even at the group level, although I don't recall. I should also mention that FSL Randomize has one particularly great perk, which is called TFCE, or Threshold-Free Cluster Enhancement. It's a way that allows you to just specify, I want my clusters to be corrected at the 0.05 level, family-wise error, without you having to say, how high up a threshold do you want? Remember when we spoke about random field correction using Gaussian random field theory, we said that we have to pick a threshold high enough that the expected value of the Euler characteristic, right, pretty much approximates the probability of getting one or more false activations. Now you have to pick where that number is, and in fact, we will discuss a lot the issues that come with this in the remainder of this lesson. TFC does away with that. Now, it does use some hyperparameters that are hidden in there that were estimated on the basis of prior data. So long as those are tenable, then you can actually just say, just correct it at 0.05. Just give me a map that is 0.05 corrected family-wise error, and you don't have to select the so-called cluster determining threshold. You don't have to say how high that has to be, which for most times is something we do in a fairly arbitrary